All right. So new chapter today. We are going to talk about carbonyls now. For most of the rest of the class, we're going to talk about carbonyls. Those are our largest groups of functional groups left. So today we're going to talk about aldehydes and ketones, and then start looking at why they react the way they do. And then our chapter after aldehydes and ketones will be carboxylic acids, but that probably won't be until after the midterm, which we decided was my Gen Chem students asked me about their midterm. And that reminded me that this is week 4, which means we're getting close to midterms already. We're doing it on the 19th, so the Tuesday of week 7. So 3 weeks from today. Sorry? We'll take it in lab, probably, or during lab. Probably not in lab because that's not a comfortable place to take a test, but we'll use that time slot. It'll still just be the 2 hours for the purposes of SAS and accommodations, but we'll just use that time slot. So we don't use a whole week to take a test, basically, because we'll do a review the morning of, and then. All right, so first things first.
Okay, I know why we were wrong, and I should have thought about it harder, even when I was in development.
So you all both recognize that this is an activating group, this is a deactivating group, so nothing's going to react over here.
Yeah.
So then it's an OP director. So then we're just looking at Sarah. Excuse me. Thank you. Right, so that one I feel like we don't need to spend too much time on because we know it's steroids, we just forgot to think about that.
Yeah.
Why does 90 degrees feel super hot if our body temperature is 98.6? It's because our body produces heat. It doesn't just maintain its temperature, it produces heat by breaking down sugars, right? Those are all exothermic reactions. And so our body is evolved to be really good at maintaining that internal 98.6 temperature because that's the temperature where our proteins work best. If you get proteins too far out of that range, then they start to unfold incorrectly because we start winding up with other side reactions happening, basically. So our body is trying to maintain 98.6, and it's evolved to do so based on how much heat it loses at ambient temperature, which is usually between 60 and 90. Our body has ability to compensate for that, but especially at high humidity, our number one way of keeping our temperature down is sweating, and sweating doesn't work well at high humidity. So basically, 90 degrees feels really hot because our body's still trying to break down sugars because that's how our body lives. And so it's still producing heat, even though it doesn't need to be producing as much heat to maintain the temperature. It's still producing that much heat because we need the energy.
Makes sense.
It does, in a roundabout sort of way, when we think about it in terms of thermodynamics and proteins and everything. And then 3D.
Like have like parameters activating or deactivating, but we don't have parameters like the toe or T. It's like you can't make them all. Which one do you?
So you go with the strongly activating one, the most strongly activating, and in this case, the most strongly activating is the OH. But we can't, and we know that OH means OP. But one of our ortho positions is already occupied by the bromine. One of our ortho positions is already our para position is already occupied by the nitro group. So the only spot left is the other ortho.
So you wouldn't get all of the ones that we did. Or would you still get three?
No, because you're never gonna put it meta to an activating group. The other two positions we could put it are both meta, and we're not gonna push off a nitro group or a bromine. Our electrophilic aromatic substitution only applies to hydrogens. So you're right that there's 3 carbons where we can put it, but only 1 carbon that is ortho or para to our activating group. We have more than 1. We should always be looking at whatever is the most strongly activating is the one that you need to be paying the most attention to. And then you look at sterics if there's more than 1 option. I did not actually look at your answers yet. I just skimmed the questions to see which ones we need to go over, and I saw that the multiple choice question. And this question, the way it was written, this is similar to the way if you took I've never taken the MCAT, or even spent a whole lot of time looking at what types of OChem questions are on the MCAT. But this is the way that the ACS standardized test, the American Chemical Society, or the chemistry GRE questions are written. You'll just get, here's a reaction. What is your, and it's multiple choice for your products. So I pulled this, I think the Klein textbook has a section at the end of every chapter that's like, here's how standardized test questions on this material would look. So I think I just pulled this straight from that. When you're getting ready to take MCATs or the TAT, then you just want to get a study material that is specific to that test, because every test is going to have things like the DAT and the MCAT are probably pretty similar.
Yeah. All the same.
Right. And probably similar to, probably vet school, probably, do they have their own or they take the MCAT, you know?
They might take the MCAT. Google.
Either way, it's gonna be very similar
Yeah.
to the MCAT, in the structure of the questions, but when you take the standardized tests when you're an undergrad applying for grad school are on another level compared to like the SATs.
The US veterinary required record examination,
GRE.
Rats.
And then there's probably sometimes, so GRE is like the grad school equivalent to the SATs. There's an English section, there's a math section, and they're both general. But then there's like the subject test. There's the GRE subject test, which are like the SAT2s. If you had to take those. That's probably one specific for that. Okay.
Right.
I bet the Casper is probably a similar to the MCAT, but oriented towards.
16. That's it.
Open response, 60,
Oh.
65 to 80 open response questions is a lot. The GRE for chemistry was probably the single hardest test I've ever taken. The GRE, the regular GRE, felt like taking the SAT. I don't think I even studied for it, and I think it's a lot of like, that's what business majors take to get into MBA school and stuff like that too. So if you're decent at reading and writing and you know your basic math backwards and forwards, then you'll be fine. The subject GRE, it was a 3-hour test that was on everything, every chemistry class I'd taken, including some I hadn't taken yet.
Oh.
So that one I spent a whole summer prepping for. When I was doing undergrad research. My undergrad research was in Santa Barbara, and I didn't know anybody in Santa Barbara. So I had housing with random people that I'd never met before. So I would finish work, I would go surfing for a couple hours, and then I would go study until I went to bed. And that's just all I did for a whole. Streaming wasn't even a thing back then either. So there was like no, like, yeah, I had my computer, but there's no distractions really.
Yeah.
But that one was a really hard test. It was satisfying though, because I felt like I really did earn my degree because I knew all the stuff by the time I got there. But anyway, MCATs are a whole different beast. Med school, dental school, vet school are all a whole different thing. Med school, it's pretty competitive to get into, but I don't think it's the same level as medical school as far as like you get assigned where you're going and things like that.
But it's more competitive because there's like a third as many schools that
Right.
and it's like twice as many applicants compared to
Per person or per school.
no, just like in general compared to like that. I found out that oral surgery school and dental school are different, and then it's not you get your dental degree and then the residency oral surgery. So, but they're both in the same school, so it doesn't put out too much of a red.
Yeah, and medical schools and dental schools and vet schools in general, once you're in, they take care of you.
Yeah.
There's not nearly as much attrition rate as there is grad school for masters and for PhDs. There's a lot more attrition because there's very little hand holding. It's very easy to get in, and they don't care if you finish.
Yeah.
As opposed to medical school, once you're in, they've invested a significant amount of resources in you and they want to keep you there and make sure that you succeed. Yeah. Which is just very different. This was neither of you, but I saved this picture from several years ago because this is somebody's work answering questions. And I actually kind of like it because it explains their logic and what they were thinking, but it also reminds me of but he's got a little bit of a murder war going. No.
It wasn't?
No, if I'm remembering who this was properly, I think her name was Christina. But it was, it's organized very logically.
Yeah.
It's just, there's a lot going on. She was trying to keep track of everything that was going on.
Yeah.
That's not a bad way to do it, as then usually you would then clean it up.
Yeah. Yeah.
All right. I still use that as an example, even in my Gen Chem classes. They're like, hey, if you want to answer a test question like this, that is fine, because at the very least, I will be able to give you some partial credit because you said some things that were right.
Yes.
Even if you settled on the wrong final answer. All right, let's talk about carbonyls. So this is just the carbonyl row from that functional groups poster that we started back learning from back in Gen Chem, really, yeah. But they tends to fall into two categories, which in the categorization will make more sense now that we understand the chemistry a little bit better. Class 1 carbonyls are the ones that I have outlined in red here. The class 1 carbonyls, what makes them class 1 is that they have a good leaving group attached to the carbonyl. Right, so an OH is a decent leaving group. This whole group is a leaving group. That's a really good leaving group. That leaving group would be a deprotonated alcohol. That's a pretty good leaving group. And the amine's a good leaving group. A halogen's a good leaving group. So the fact that we have all these leaving groups means that they can go through substitution reactions pretty easily. We can swap an OH for an amine pretty easily with these. And so that's going to be the most common reaction we see out of these class 1 carbonyls is we can basically interconvert between any of these different functional groups by just changing the conditions. That's not the case with aldehydes and ketones. So for starters, one of the things about all these leaving groups is the carbonyl carbons all have the same oxidation state. So we're not doing any reduction or oxidation here because if you remember how we assigned oxidation state, it was, okay, how many electrons does this carbon own compared to the periodic table? And we basically just said, okay, treat everything like it's an ionic bond. Whatever's most electronegative gets first dibs. So for all of these carbonyl carbons that are class 1 carbonyls, assuming R is another carbon, then we get, okay, well, it doesn't own any of these electrons. It doesn't own any of the electrons between the carbon and the leaving group. It only owns electrons between the two carbons here. So basically it owns 1 electron compared to 4 on the periodic table. So that would be a +3 oxidation state. And all of these are going to be +3 oxidation states. They might be +2 if your R group is a hydrogen. Right, because that R group being a hydrogen means that this carbon is more electronegative than the hydrogen. It gets both of those instead of splitting them. But other than that, that's one of the reasons why it's so easy to go back and forth between these is because we're not doing any oxidation or reduction. The class 2 carbonyls are just aldehydes and ketones. The only reason they are separate functional groups is because of that oxidation state. Because aldehydes have a different oxidation state than ketones. For the same reason we were just talking about, and that means that the aldehydes will react a little bit differently than ketones. But for the most part, because they don't have a good leaving group, most reactions that we see for aldehydes and ketones are going to be addition reactions. What we're more likely to see with aldehydes and ketones is we break the carbon-oxygen pi bonds and we add something to both sides. So pretty similar to our addition reactions we saw with alkenes, just with a little bit more specificity because we're not breaking a symmetrical pi bond, we're breaking a pi bond between a carbon and an oxygen. So that the fact that our pi bonds between a carbon and oxygen means we have a charge distribution, right? We have partial charges there.
Yeah.
What's the partial charge on the carbon?
In both cases,
In both cases.
but it has. Like on the left, showing that that's a hydrogen, are we setting R as hydrogen?
Yes.
Okay. So then. It's gonna, 2.
So not oxidation state, just in terms of like partial charge. Like in terms of like polarity.
Oh,
What's more electronegative, oxygen or carbon?
oxygen. Oh, so it's partially positive.
So carbon's partially positive. And oxygen's gonna be partially negative. So that's gonna make it a different type of addition reaction. Hey, can I help you? Yeah, grab a seat if you want.
So you said like class 1 is because it has a good leaving. So class 2 is based on the oxidation state, right? Well, based on like oxidation state, not which is the front of the comparison.
So yes, your class 1 carbonyls all have the same oxidation state because it's a little bit of a chicken and the egg situation. You have a good leaving group, and that what makes a good leaving group is that it's more electronegative carbon, so it gets bringing the electrons with it. So because the good leaving groups are all more electronegative than the carbon, that also means the carbon is going to have the same oxidation state. So it's sort of circular logic a little bit. They're all tied together. It's all based on the electronegativity. Versus the aldehydes and the ketones, the class 2s, hydrogen's not a good leaving group, neither is carbon.
Yeah.
So even if we tried to get this carbon to react, it's not going to react the same way as the class 1 carbonyls because it doesn't have a good leaving group. It's still going to have a partial positive. All of these carbonyls have a partial positive, right? But the difference is it doesn't have that leaving group. So we break the pi bond instead, and we're going to do addition reactions. But it's going to be different than our alkene addition reactions because we have a partial positive and partial negative. Because remember, our alkene addition reactions, it was symmetrical, so we kind of had to choose how we're going to do it. And that's when the Markov-Nikolov rule came in, right? We spent all the time on Markov-Nikolov rule. The reason we had to spend so much time on that is because we couldn't just look at it and determine where partial positive was. For aldehydes and ketones, the fact that we've got a partial positive on the carbon makes it really easy to see what's going to attack where. All right, so just breaking it down again to review, the difference between the aldehyde and the ketone is the ketone is a carbonyl that's in the middle of a carbon chain versus aldehyde that's at the end of a carbon chain. So the only way we get this H is if it's an aldehyde, because we're limited to the 4 bonds per carbon that we're used to. So there's no way to have, it's going to feel wrong even to draw it. Like that should look really wrong to us by this point.
Yeah.
But you basically pull out the carbon.
Yeah, so this is not drawn as a carbon because again, we just assume anything not drawn as carbon.
Yeah.
But the fact that we have a hydrogen attached to a carbon double bonded to an oxygen makes it an aldehyde. A carbon double bonded to an oxygen that has 2 other carbons on either side is what makes it a ketone. And we do name them differently because they are going to have slightly different reactivities too.
What is the precaution of basically kind of proving them like this? What are you trying to protect yourself for aldehydes and ketones?
So it's less about protecting and it's more about they're going to undergo similar reactions to each other. So both of these, they're going to have some subtle differences between the two. But if you put them under similar conditions, they're going to react in a similar way because they have similar bonds.
So basically the way you can differentiate them or identify them individually is basically through kind of defining their
Exactly.
group levels and kind of people.
Exactly. So we call them functional groups. And the different functional groups are basically what's going to mean, even though you have the same number of carbons, that molecule is going to react very differently than that molecule.
Yeah. I think I've always heard that from my professors of chemistry in high school. They always basically kind of.
Yeah, exactly.
Experimenting. A lot of people kind of not know how to differentiate.
Right. It's a little bit, it's similar to the taxonomy in biology. It's different in that it's more based on the fundamental principles. But it's similar, like, okay, well, we can say that all felines have these sort of characteristics. All ketones have similar sort of characteristics as well. There's ways that we identify them, and then there's behaviors that they have that are going to identify them as well. So just some examples, because we know we like good examples of our functional groups every time we learn a new functional group. Class 2 carbonyls that show up all over the place. Vanillin. Remember, if we got rid of these 2, then we have benzaldehyde, which is almond flavoring. And if we
actually add all the flavoring to a lot of raw steaks.
Yeah. Well, it's cheaper than vanilla because it's a simpler molecule to make, and it gives it a more well-rounded. Because if you just add vanillin, like real vanilla extract is going to be vanillin, but it's going to be a lot of other compounds that are kind of similar that'll hit similar receptor sites on your tongue, but not the exact same. So that's why vanillin, artificial vanilla flavoring, is a lot more one note than real vanilla extracts. And so that's one of the ways that you can get around having to use real vanilla extract if you're making cheap frosting is you use vanillin, but then you also use benzaldehyde, which is easily made synthetically and easy to work with.
Menacing there in the kitchen.
I mean, if you go to the right kitchens, they talk about that kind of thing.
So good.
Yeah. Cinnamaldehyde, carbone. So remember this is the example that where the R versus the S gave us very different flavors. Do you remember what the other one was? So R carbone is spearmint, S carbone is caraway. So very much more savory than we usually think of mint. We usually think of mint as being in the sweet applications, at least in the US. I think they use mint in more savory applications in the UK and worldwide. I think it's pretty common in Indian food to use mint in savory applications. But yeah, very different, but same structure, just with that opposite. We get the mirror image. And then it shows up. One of the reasons that all of these hit different flavor profiles in your mouth is because they all occur in nature. So our bodies have evolved, humans have evolved to have different receptors that detect things.
Yeah.
Right? Things that don't occur in nature don't typically have much of a flavor because we don't have a receptor site that's evolved to detect it. Hormones fit the same thing. And then some of the really small ones, these occur in nature to some extent. But we see them more frequently in labs. Although they do occur in small amounts in normal metabolic processes, like we've talked about. Formaldehyde, when your body breaks down methanol, it makes formaldehyde, and that's actually the formaldehyde that causes the bigger issues in your body compared to the methanol. And we actually do produce. Anybody gone on a paleo diet or have friends that do things like that where we talk about ketosis? So keto diet, when you go into ketosis, that means that your body is producing what in biology they call ketone bodies. But basically you're just making small molecule ketones, which aren't necessarily really good for you. Acetone is a carcinogen. But if you go too long without ingesting any carbohydrates and your body's living exclusively on stored fats, the process of breaking down fats for energy winds up making an excess of these acetyl-CoA that feeds into the electron transport chain. The problem with acetyl-CoA is that if you're using too much, your body needs that coenzyme A for other processes as well. And if too much of it is being held up in your acetyl-CoA, because that's the only thing that you're doing to make energy, is breaking down fats, then you can't have some of those other processes happen. So your body will free up acetyl-CoA by taking the acetyl group and basically breaking it off and making acetone. So when you go into ketosis, your body makes acetone, and it's actually noticeable. Not only like it'll show up in your blood work. But if somebody who's been on one of those keto diets, like really hardcore, you can actually smell acetone on their breath.
Really?
Yeah, it's not super healthy long term. Although you have to balance that. Is it better to be in ketosis and losing weight, or are you healthier being more overweight? If your choice is being, okay, well, it's a little bit of something's going to kill me. Is it going to be the acetone or is it going to be the obesity? So it depends on there's not a single answer to is that a good thing or not. It depends on your exact situation. When we're naming these, we know our impact nomenclature by now, right? Find our longest continuous carbon chain that has our functional group in it. Name it like it's an alkane. If it's an aldehyde, we're just going to drop the E, put Al. So similar to an alcohol, if this was the alcohol, it'd be butanol. If it's the ketone, it's butanal. Okay. The big difference is with butanol, we have to specify where our OH group is. So we need to add that locant. So we'd say 1 butanol. We don't need that for an aldehyde though.
Because we know it'll be on.
It has to be at the end of the carbon chain, so it's always on carbon 1. If you get a weird case like this, cycle, where we have, you can redraw it up here, in the no man's land down there. Then our longest continuous carbon chain that has the functional group is single carbon, but we don't name it as methanol. We'd say cyclohexane, and we just use carbaldehyde to say that there's one carbon attached to it. So instead of benzaldehyde, it should be benzene carbaldehyde.
Okay.
If we're following our rules carefully, but benzaldehyde is good enough in that case. So if it was like that, it'd be cyclopentane carbaldehyde. And if there was anything else attached, let's say that this was coming out of the board towards us. Let's say we got a bromine over here. We can say that that's, well, we have two groups now, right?
That's too far.
1s3r.
Okay, 3R.
So priority 1, priority 2, priority 3, and the hydrogen's into the board. So that's, you're correct. 1s.
Oh, but that one's normally, so it's gonna be also this.
So 1, 2, 3. So that would be R, except the hydrogen's coming out towards us. So we need to look at it behind the board. So it's also going to be S. You're correct. 1s, 3s, 3 bromo, cyclopentane, carbaldehyde. Right, and then this is the most complete way to name it. If we get 1s and 3s properly, that also tells us it's trans, but you could throw trans in front there. They indicate they're on opposite side of the ring. But again, because we had both of these established, we don't really need that. It's a little bit overkill.
Is there a dash? It's like in particle behind.
Well, remember that most of the hyphens that I add are just for me. So
It's not.
if you want one, go for it. I'm not gonna mark you down. But the way that it's drawn here, it makes it all one word. So the textbook says make it all one word. I don't like it when they're all one word either.
Like when you make a phone number, just all one number.
Yeah, you can do that, but why?
Yeah, exactly.
All right, so aldehydes have that wrinkle that we have this carbaldehyde idea. Ketones are actually simpler, except for the fact that they can be anywhere in a carbon chain, so we will need a locate to say where the ketone group is. All right, so for ketones, instead of Al, we're adding O-N-E. So it's not butane or butanal, it's butanol. And then we'll either throw our locants in front, or we can put it in the middle of the word if we want, like we've seen before. Especially if there's an alkene and a ketone. So for instance, we have that molecule. We're definitely going to want to put our locants in the middle of the word so that we can put a locant in front of the alkene portion as well, right? Because this would be 1, 2, 3, 4, 5. So it's going to be pent or penta 2-O. or sorry, no, we do need to put pen 10 2 ohm.
And when you're sitting. For reading that time.
1, 2, 3. Yep. 3 pen 10 2 ohm. And then we would also want to specify E versus C. In this case, right? So we would. Z is.
Oh, wait, no, sorry, I just that.
Yep.
I think it's the other one.
E. Indicated against. And so. This is more common if it's a simple molecule. Because it's easier rolls off the tongue. Easier to say 3 heptanone versus heptane 3 ohm. But if it's a more complicated molecule, you might have to do that.
Right.
Like we've seen before. All right, the old school name, the way to name these. And this is one that you still see in the hardware stores in particular. Is you just name what's attached to each side. We're just going to call this a ketone. And we just say, okay, well, on one side of the ketone, I have a methyl group. On the other side of the ketone, I have an ethyl group. Methyl ethyl ketone. Which is still sold as a vegan dinner. Not in California. Because they're cheap organic molecules that they got from refining petroleum, so they were a byproduct of petroleum. You could add methyl ethyl ketone into your gas tank. Your gas tank. I don't know if it would run, if your car would run if it was 100% NEK, but you could definitely use it to boost the octane rating.
I've seen like if you add to your chains and they make it like last longer.
Yeah, exactly. You can do that with almost anything organic. Some of those ones have additives in them that'll actually help it be better for the engine. So if it burns cleaner,
Right.
then that's usually going to be better for your engine long term.
Yeah.
One of the big issues with our snow blowers up here is that none of them have, they're not fuel injected, which means they still use carburetors. And engines that use carburetors don't handle ethanol gasoline very well. Ethanol gasoline has a little bit higher water content in it and produces a little bit more water per mole when you burn it. And so you wind up with your carburetor rusting out and getting corroded from it.
It starts to spit.
And it starts to spit. And so you either have to replace your carburetor at that point or buy a new snowblower. Doesn't affect fuel injected cars. So modern cars are fine. Anything from about the mid 70s forward is fuel injected. And so cars run fine on ethanol gas, but snowblowers, dirt bikes, things like that, yeah. If it was something like a dirt bike that was more expensive than a snowblower, then we probably would too. But in the dead of winter, I'm not driving down to Carson City to buy ethanol brand. Yeah. That is the better option, but or get an electric snowblower.
They make those?
Yeah, they do okay.
This little, ketone will do the same concept they're doing, but 65 or.
No, so this is not an alcohol base because alcohol has an OH group. So the OH group is part of what makes it not burn so well for the older engines. This is just like I said, this is more often used. In fact, this probably wouldn't be cost effective. If I had a bunch of leftover methyl ethyl ketone, I might dump it in my gas so I don't have to get rid of it some other way. But I'm not going to go out and buy it specifically to add to my gas tank because that's actually going to be more expensive than it's worth. And again, they don't sell it in California anymore, but if you go to that hardware store that's on Kingsbury Grade, you can still buy NEK as a paint thinner. It works pretty well. All right, thanks for stopping in. All right, so let's do some practice, more practice nomenclature. Just because this is like nomenclature in OChem, it's like conversions in Gen Chem, right? Can never get away from it, so we might as well stay current. Okay. Any stereo centers in there we need to worry about?
Great question. The. The aldehyde. The carbon that attaches to the oxygen, it doesn't have any.
That's you right? That's clear.
Yeah.
Yep. That carbon, so identical substituents.
The other two have hydrogens.
Yeah. So identical bromines, three identical, so we're all good there. If it was not dibromo or dimethyl.
Yeah.
Then we would. Two hexanone. It's our parent molecule. 3,4 dimethyl. So priority up for carbon 3. Oh, you're right. 3,4,5 trimethyl.
But does it matter about moving it? Oh, no, it doesn't matter. I keep it.
Good catch. Not tetramethyl. So my brother got Valence a like keychain. It's not really keychain size. It's like this big handheld Tetris game. And
Really?
it's been a big hit
That's
in my family.
Yeah, it was her birthday.
It was good. She had a lot of fun.
Good.
She teared up when she opened her console.
I'm sure that's so exciting. Did we have to? Orange.
Then we have to do RNS for carbons 3 and 4. So for carbon 3, we've got highest priority, second highest, third highest. So it looks S, but it's backwards. So it's gonna be 3R. For carbon 4, highest priority, second, third. So it looks R, but again, it's backwards. 3R, 4S, 3,4,5 trimethyl, 2-hexanol. This one's tetramethyl.
But we didn't learn how to manage ketones. We did learn.
What's our longest continuous carbon chain that has the ketone? Is cyclopentane. So it's gonna be cyclopentanone.
Don't be able to say where.
Just like the alcohols, that's our dominant functional group. That's carbon 1. So you don't really need to specify it. If you're uncertain about it, you can say 1 cyclopentanone. But just like when we say bromocyclohexane, we don't need to say 1 bromocyclohexane because it's applied. But no stereochemistry here. So that's it. No sort of stereochemistry here either. And only one branch. Trickiest thing here is its longest continuous carbon chain that has the aldehyde. So it's going to be pentanal. And then it's going to be 2-propyl. Then it's our. Not only is it a weird cycle group, it's also got that. Got the name is carbaldehyde. We have the ring structure that has just a single carbon with the aldehyde attached. So that's going to be cyclobutane.
Because you're long, because for this one, your longest continuous carbon chain is this, where it excludes the.
Right. So, but we don't name these as methanol. We don't say cyclobutyl methanol.
Right.
Other than you could. That's not the way, the accepted way to do it, though. I would say why not just do that, but they didn't consult me when they were coming up with the rules. So cyclobutane carbaldehyde. Now, as soon as there's 2 carbons attached, then we don't do that anymore.
Right.
So if it was like that. So typically the textbook that I get most of these examples from clearly writes out the hydrogen on an aldehyde, so you don't forget it, but it's not uncommon to see it written like this too. You just have to realize the carbonyl at the end of the carbon chain has the hydrogen attached as well. But because this is 2 carbons attached, we would say it's ethanol, and then just say it's cyclohexyl ethanol. But when it's just a single carbon attached, we just use that carbaldehyde suffix.
Like, oh, that's. station.
So we would say it's ethanol is our parent molecule, it's just these carbons there. So then we could say 2-cyclohexyl. You don't even really need to specify the two, because you can't put it on carbon one, it still have to be an aldehyde. All right. Let's take our break. Let's come back at 11. We'll go the other route. I'll give you the name, you draw them, and then we'll start talking about reactions.
That's what it's for the projects, yeah. The like physics. I love Kathy because of she took that sheet with my class actually, I think. Just do it, you can get it all on one paper. She's like, yeah. Nice. But now we're a little better off with this. Yeah, me too, I'm right. I was like, we need you, what do you need?
How's it going?
I don't want to interrupt you, take the break.
Yeah.
What's the result of that poll?
It looks like a lot of the people can do May 30th,
How many is left?
14th.
No, book it.
Okay.
And we'll see. Like, I don't know if I have to be there or not.
Well, I think like we might have to have a different, and we might have to get in with that to go with that. 'Cause I don't know if they can just go
Yeah,
without,
yeah, I heard that's the question.
yeah,
Okay.
maybe 30 months.
I'll book it if it turns out that
We can like hear.
it's lost, cancel. Okay, cool. The only available time is 10. That's definitely pretty early.
That's probably when we start. Yeah, but I feel like, I don't know, I don't think people are expecting to have a leisurely Sunday morning if we're driving 10 hours. Is that mean?
5 hours now.
It's 5 hours each way.
Where is it?
On our AD.
Oh,
They leave at 5 in the morning.
Yeah. If we have a bucket with the van.
Are those 14 people aware that that's the time?
I don't know if we have a. I'll just sleep on that yet, but. Yeah, I don't know. I had messaged. California Academy. And they said, no, you're too old. We only offer it for these grades. So that was really lame. So they're kind of out of the question. So I couldn't get them to give us any discounts, but I'm gonna look into a couple more places, see what else I can do. Anything maybe closer than Monterey.
It is asking for a lead teacher.
Yeah. Sorry, wasn't wondering.
When is it?
Saturday.
No, baseball.
Yeah. I mean, we did like the half bus, right? Yeah, I know how many rows are in that? I don't know. We can all bring those like dog things, and then sleep in a row. And then 5 o'clock will be nothing.
All right, I'll just put my name in here. Just to secure this, because,
Yeah. Well, you can ask Harry Hole, right?
uh. Yes, I can ask. Let's see, okay. That's nice.
Yes, thank you.
All right. You've got the names, let's draw the structure. Those ones usually go quicker, so it's a good view. Did them from right to left for some reason. Right.
Yeah, I got pictures.
The only thing really tricky about this is something is stereochemistry. We've been dealing with that for a long time. And as far as you all drawing the aldehydes, I'm fine drawing it like this, or if you wanted to add the H, go full credit. No reasonable chemist is really gonna fight you on that either way. Does the science level going to be working or?
Yeah, but not really.
Not yet.
No,
You are science level.
I'm.
Oh, you're going, okay, so.
But Carl's, I sent out a quote for like 2 different weekends, both Saturday and Sunday.
Mhm.
And so we found a day that we're just plenty of the like, oh, perfect. And then Carl went on the website that June 20th was no longer available at Monterey. So then he was like, there were these days left, and I just sent out those. So now me and Carl can't go. But everybody else people apparently, so I'm not.
As long as they find a lead teacher.
If we find this teacher, yeah. I am teacher. I'm gonna talk to students, and she's already going with the group this year, but maybe we just like that.
Maybe tag along,
Yeah. So,
might be easier.
yeah, because if she already has to be there, add some kids to it.
I mean, yeah, you're never gonna be able to make everybody happy, right? So,
No, yeah, they.
all right, so quick recap of how we make aldehydes. We've seen these before. We had 3 different reactions that will allow us to go from primary alcohol to an aldehyde through an oxidation, right? We can't use chromic acid or the sodium dichromate. But we had 3. We had the PCC, which was the pyridinium chromo something or something chromate. I don't remember what exactly, but all 3 of these would oxidize a primary alcohol and stop with the aldehyde.
Yeah.
The DMP was the Des Martin pyridine reaction, which is that iodine containing molecule. I believe this one was called a Swern oxidation, if I remember it correctly, but don't quote me on that.
Was that this? That was this order. I think that was the end.
That was the end of last quarter. We covered alcohols. We can make aldehydes if we do ozonolysis as well. Right, so this slide is just how we make the aldehydes. The reactions that we have to have aldehydes as a product so far are the oxidation of primary alcohols, ozonolysis of the right alkene, or if we did the hydroboration oxidation of an alkyne. Because the hydroboration oxidation was our anti-Markovnikov hydration reaction that then rearranged itself. So remember, the first step would look like, so with this, and we did Br2H, and then followed it up with our H2O2. The first thing we would get is the enol, which then rearranges itself to the aldehyde.
Right.
So we're really going back a long ways, having to think about anti-Markovnikov, and but the net result is an aldehyde there. If we wanted this reaction to give us a ketone instead, we wouldn't use hydroboration, we would use, what were our other options?
That would go into.
That would be regular Markovnikov.
Oh, there has to be a lot of membrane.
The other first addition reaction we added was the oxymercuration, right?
Oh, yeah.
So if it was oxymercuration followed by acid, I believe, that's what we use. No, sorry, sodium borohydride. And we had to use sodium borohydride to reduce the mercury and get it off. Fine. Either way, we can go back and review that. Actually, it's on my next slide. That's right. This one, because it's the alkyne, we need to do the mercury with our sulfuric acid. And so making ketones, oxidation of secondary alcohols, ozonolysis of different alkenes, acid catalyzed hydration of alkynes, or Friedel-Crafts distillation is the one we just added.
Yeah.
Right, so that's a very specific case that only works if we're trying to add a ketone to a benzene ring, but it is still an option. Let's see if we can remember all the last two slides. It's less about the recall and then more about putting it on paper to jog your memory. So you can check your notes.
We're ready, what we all share.
Yes. How do we do it? And for these type of questions, I'm not gonna get too hung up on,
What do we have?
no, I'm giving you options. But you see, it was only two slides ago and already I can't remember what smart oxidation, what exact conditions for, but I know that it exists. And so I'm more interested in you remembering how to do these things and then you can go back and find it on your cheat sheet or in your textbook. Than I am just remember all of the exact reagents that are used. Right, because in this day and age, what's the point of having perfect recall when everything is on your phone, in your pocket at all times?
This one. It was to these are two sides, and these are H. Oh, no. Wait, no. Yes, you can.
If we wanted to make the aldehyde and put carbonate here, we would do borate. Hydroborate approach.
Okay. Yeah,
But because we want it to be more common, so we're using the acid catalyzed hydration. Oh, that's D. There you go.
yeah. So then on this one, we use. One, two. H2O2 on the. And language.
Yeah. In order to oxidize the boron and get it off of our molecule, we needed to deprotonate the hydrogen peroxide to make that super reactive.
Next one.
If I remember correctly too, with those salts, there's lots of mild reducing agents you can use. EMS is just the most common one.
Okay.
But a different type of smoke might have it. The most important thing is to recognize the ozone. As soon as you see the
Yeah.
ozone, it only does one thing for us.
Here are the ozone layers.
It did, which makes sense. It's a naturally occurring feature of our planet anyway, based on the magnetic fields and the cosmic radiation, which is just a fun thing to say. Sounds like a comic book superhero power, cosmic radiation.
This one, the only words to find out.
Yeah, so it's from the perspective of how do we make a ketone, it's a fairly narrow reaction. But this was one of our electrophilic aromatic substitutions that we did.
Yeah, so, and then instead of saying R, you want us to draw out the others.
Yes. If we're trying to make a specific group there, you could say that this equals an isopropyl group equals R, and then just use R instead. But that's probably more writing than just drawing it out.
Yeah.
So there's a point when you're doing algebra where it's worthwhile to redefine your variables to simplify things.
Yeah.
And it's not always. Sometimes it's easier to just do it rather than rewrite it.
Yeah. In Gen Chem, they often take our 403 final with the crayon and this past the mountain water. Just to piss Carl off. And I really have to make them all and they're all in crayon. What if you got something wrong? So you can't erase that. I think Abacus actually does really good crayon because he does like the scrap paper and then like the version on the real paper. I did mine right. Why? Because I mess up a lot.
So she didn't actually use the crayon, is what she said.
Practice. I'll do it. Maybe for like a couple answers, but not for the whole thing. No, that's not.
There's lots of good jokes about crayons. Usually you hear them applied to Marines, but sometimes I've heard them applied to pre-med students.
Really?
By the snootier chemistry instructors. It's the hardest part about teaching gen chems, keeping the pre-meds from eating the crayons.
Yeah. I've heard that about the, Marines.
Marines.
Yeah.
Hockey players are a good target too.
Yeah.
All right, here's gonna be our main mechanism for class 2 carbonyls. It's the nucleophilic addition. Our addition reactions for alkenes were all electrophilic additions. We started with something that was attracted to the pi bonds. Because the pi bond was symmetrical, we didn't have a partial positive. We could have a nucleophile come in and attach. But for our carbonyls, our class 2 carbonyls, we're going to do nucleophilic addition. So you just need any nucleophile. Works here. And it's just going to attack the carbonyl carbon, but then we need to make room for the new electrons. So we wind up making an oxygen with a negative charge, which then just gets protonated. So step 1, expose it to a nucleophile. Step 2, proton source.
So do we draw the arrow from the negative, or does it have to be there?
Either way, negative charge or an electron pair. Because a negative charge is an electron pair.
Right.
And it's same for the proton transfer. Right, and then the bottom part is just to show how good of a target this is. If you have a carbonyl, this is just acetone. It's drawn as a triple bond, but that's just as a result of the program that I used to make the figure.
Okay.
It's a good segue into what we're doing in lab today. In lab today, we're learning how to make molecules in 3D. So it will be helpful if both of you have computers.
Yes.
I don't know if your iPad will work. If you have a computer too, cool.
I kill my back for fun.
It'll pay off today with this lab. It's way easier for you to do it while we're working on it than to go home and work on it later. But so we're going to practice making these molecules, and one of the nice things about making these molecules is that then we can feed it into a program that basically is going to go through and find the lowest energy configuration of all the orbitals by mixing them all together and hybridizing them all. And then when you do that and you look at where all the electrons are in the most stable state, you can get a charge map. Which is basically where you likely to see partial positives and partial negatives. So blue is negative, then it goes through the green is neutral and red is positive. So this shows pretty strongly that carbonyl carbon is a really good target, more so even than the hydrogens that are on either side, because it's directly attached to an oxygen. So that's just showing why it's a really good target. And it's planar too, which means sterics aren't going to get in the way too much. You can have something attack either side, which also means we're likely to see, if we make something that has a stereo center when we do this, we're likely to see equal amounts of RNS. Nothing new, just recapping. So
I can feel it.
in general, so this applies to all class 2 carbonyls, ketones, and aldehydes. But in general, aldehydes are going to be more reactive because they have a partially stronger, partial positive. So remember that, go ahead.
The arrows.
So that's a physics way of representing magnetic charge.
Do we have the mechanism on your device? Is it two metals?
No, it's not. I just switched out the bottom. So because carbons, alkyl groups are electron donating, right? So that's actually going to mitigate this to make it not as strong of a partial positive because we have two ways of donating electron density. That's what the red arrows are showing.
I used it last week, because when I looked it up, that's what showed up. I didn't 100% know what they meant.
So basically, it's just showing where the electrons are going to be moving. And I actually think that this is done, I think in physics, they show the direction a positive charge moves.
Yeah, that's true.
So I think it's actually backwards. It's a physics notation, but we're using it wrong.
Because we're saying where the electron.
We're saying that they're donating electron density towards that partial positive.
Where the electron density.
Right, so because the aldehydes only have one electron donating group to help stabilize that partial positive, they're more reactive. They have stronger partial positive.
I saw them and I didn't understand them, so.
I think it would actually probably make more sense to draw it like this, showing that you're donating electron density. But then it actually looks like it's an actual mechanism step and not just showing. So
Right.
I understand why they used it, that notation, but I don't like it.
Easy. So we have to have these memorized. What?
Well, we've been using them since
We have to really
October.
try all the possible.
No. No, but if I gave you, NaCN, and I said it's gonna react with, I don't know, let's go with a simple example, like chloroethane. I would expect you to know that, oh, okay, well, that's got a negative charge, it's gonna come here, and that's gonna lead. So as long as you know that it's a nucleophile, you can recognize what part of the molecule is the nucleophile, you don't have to have it memorized. That's really all we do in OChem, right? Is track where the partial positives and negatives are.
They all follow the same pattern, which have different rules.
Yeah, there's different wrinkles.
Yeah.
And so probably the ones that are most worth remembering are we can have hydrogen as nucleophile. Right, we have our hydride sources, lithium aluminum hydride, sodium borohydride are both pretty reactive ways. And so that'll actually give us the net result of reducing our carbonyl, right? Because if we started with acetone and we exposed it to lithium aluminum hydride, it's going to do that same reaction, except we just added hydrogen here. So that actually has the net result of reducing this carbon.
So when you use hydrogen as a nucleophile, the net result is.
Correct. And usually when you use a carbon-based nucleophile as well, it's not as good at reducing because it only reduces one electron at a time instead of two. But these other the nitrogen nucleophiles, the sulfur nucleophiles, the oxygen nucleophiles, they're all more electronegative than carbon. So they're not actually going to change the oxidation state. Because you're going to replace one carbon oxygen bond with a new carbon oxygen bond, for instance. All right, so this is the mechanism under basic conditions.
Okay.
We can set it up at the top, but I didn't emphasize that. What's gonna be different?
Is it still for class?
Yes. We're not gonna touch on the class ones, probably until after midterm. I take it back. That might be a next chapter. Till next chapter. What would it look like under acidic conditions? So for instance, if we had acetone reacting with HCl. We know chloride can be a nucleophile, right? But what's our first step going to be?
The chlorine goes to the carbon that the, oh wait, no, wait, yes.
So if we did that, we would get, so we said, okay, these electrons are gonna come over here, make room. Can we do that under acidic conditions? Why not?
It's a lot of negative.
Negative charge on the oxygen. We can't have a deprotonated oxygen under acidic conditions, right? So we can't do that step first. So what will happen if it's acidic conditions? We have lots of H plus exploding around. Bingo. Hydrogen is going to be attracted to the oxygen because that's where the negative charge is, right? So our first step would look like this step. So we wind up making a protonated carbonyl. So remember, under acidic conditions, we are more likely to make positively charged intermediates. Basic conditions, we're going to make negatively charged.
And then we just.
So we just switch the order of the steps, proton transfer first and then nucleophile attacks. But same net result. And this reaction is one of many reasons why we don't mix cleaning products.
Because chloride is.
Because when you add chlorine, and actually there's another reaction that can happen too. But basically you start making chemical weapons.
Yeah.
Chlorinated acetone is, I believe it's tear gas.
I had a friend who's really into, those like ASMR videos where they mix it all together and they have like the sponges. She really liked doing that. And I was like, great, like you're gonna clear yourself. She was like, but it's, I wear a mask, I'm fine. Like, okay. And then I saw her like 2 weeks later and she was like, okay, you were right, like I'm having trouble breathing now, and coughing all the time. I was like, you probably made like lesser gas.
That's so the big one to watch out for is bleach and ammonia.
Yeah.
That's really common because you're trying to clean something and the ammonia doesn't work. So then you get out the bleach because that's the big guns, right?
Yeah.
Even after I harped on that, I had a student just a couple of years ago who was moving out of his apartment and he was trying to get his deposit back and trying to clean the bathroom. And he did that. And he said, you were right. I had to open the window and then that wasn't enough. So I had to take a break while it aired out. Actually, sorry, I take that. It's bromine and acetone. Bromine and acetone is tear. Will give you something similar to tear gas.
We should just use vinegar as last year's for that. What the heck is mustard gas? I've heard of vinegar.
Yes.
But I don't get put on the list. You're probably already.
Yes.
Salty and acid. That got me on one real quick. Bleach with ammonia.
Bleach, it'll give you something similar. True. Because it was under very mild. If you experience it just a little bit, it actually has a bit of a strong mustard odor before it burns your sinuses to the point where you can't smell anything.
Lovely. This has a little chart. Chlorinide is.
Chloramine.
Chloroform is bleach with alcohol. Chlorine gas is laser vinegar. And peracetic acid is peroxide of vinegar.
All bad things.
Yes. So bleach contains chlorine.
Sodium hypochlorite. So it's not just that it contains chlorine, it contains a very reactive form of chlorine. And so what this the oxidation state on the chlorine here is a +1, because oxygen is more electronegative.
Yeah.
And so chlorine with a +1 oxidation state is not stable. It's going to react really quickly.
So like,
It would rather be. So it'll react. Well, it's one of the reasons why it's so good as a cleaning product, because anything organic that's around reacts with it really quickly.
so like mold and stuff.
Mold and stuff, it kills things, and it also will take anything that, oftentimes if there's anything that's absorbing light in the visible spectrum, that usually means if it's organic that it has, what's the word? That it has conjugated pi bonds. And when you expose it to a strong oxidizing agent like this, you wind up oxidizing the pi bonds, and then it doesn't absorb in the visible spectrum anymore. So that's why it's good at treating stains. It basically just breaks the molecules apart. But it also breaks apart molecules you want to keep. So if you continuously use bleach on things, you wind up with shortening their lifespan too. I used to use bleach all the time when I was brewing at home, because it's a really cheap way to send. You can buy like food grade sanitizing agents, but they're really expensive. And bleach is really cheap. It's like, at least 10 years ago, it was like $3 a gallon.
Right.
So I would just buy bleach and use that to sanitize all my brewing equipment. But if you do that to plastic over a long period of time, the plastic gets brittle and breaks, because you're oxidizing plastic too.
Oh. No word of the ropes.
All right, so here's the neater version of the one we just wrote. Proton transfer first, and then nucleophile.
Well,
All right, so let's practice doing this. Part of this is to establish, is it acidic or basic conditions? So that's just going to determine our order of the steps, right? So, Grignard reaction. Acidic or basic conditions? Correct. Remember, we have to do it in 2 steps because the water is acidic enough that if you expose the water to the Grignard reagent, the water will react with it.
So we're gonna say that the ET attacks in this case?
Because it's a carbon attached to magnesium, right? So the carbon actually has a negative charge there.
That's a negative.
Correct.
It's not a swirly.
Not as swirly. I'll have you know, drawing these structures like this while I'm trying to face you as well gets a little sloppy. Good?
Yeah.
Last but not least. Are ketone reacting with HCl, acidic conditions or basic conditions?
So it's,
Acidic,
so. Would we draw water? That
wouldn't draw the water.
is the blue thing the second step.
Correct. So first step is protonate the carbonyl. Put a positive charge on the oxygen. And the second step is your nucleophile attacks. So that also is in review too. So we talked about that acidic versus basic conditions when you're talking, probably going back all the way to the enol tautomerization, right? Under basic conditions versus acidic conditions that does the same thing, but in opposite words. Cool. Well, then we're done a few minutes early. All right, so come back at 1 for lab.
Yep.
Bring your computer.
I have six. And I need food, I'm not hungry.
Well, that's a good thing. We can end it a couple minutes early.
Oh, I have honest tools. I need to. I don't even go. Yeah.